Okay, so today I'm going to be talking about regular expressions. Um, you've probably come across these at one point or another, either in the phase 1 or 2 curriculum or on your own. Regular expressions are kind of like a little, I don't know what the right term is, pet love of mine. I don't know. I like regular expressions. Not because they're not just because they're useful, but just because I don't know. I think they're fun in some way. So, as this is my last lecture at the Guild, sad face, I thought I'd do one on regular expressions. It's actually one that I've given before that I sort of dusted off and converted to examples to use JavaScript. Anyway, but I will just dive right in. If you have questions, please unmute and shout out. I'm on one monitor today, so the slides are taking up all of my screen. I may not see things posted in chat right away. So don't be afraid to stop and interrupt me. I'll try and make pauses for that as we go. So let's talk about regular expressions. But first, before we start talking about regular expressions, we're going to talk about something called regular language. Because it turns out that to get a good definition of what a regular expression is, you have to first understand what a regular language is. And regular language is a concept that was formalized by this guy in the 50s, Mr. Claney, not this guy, this guy. And Claney, Stephen Cole Claney, which is pronounced Claney, even though it doesn't look like it should be. Looks like it should be Claney. So he formalized this concept of a regular language back in the 50s. And he defined a regular language, so a language we understand, but the regular part that he's getting at is a sort of a subset of all languages, or it's a specific type of language. So we understand a language to be the subset of all possible words over a given alphabet. So this is pretty intuitive. We all know at least one language, English, and we're learning JavaScript. Some of you may speak other languages, but if you think of a language by that definition as what did it say? A subset of all possible words over a given alphabet. So our English alphabet, A through Z, can be combined in an infinite number of ways, right? Into different words. And if you take a subset of those words, a subset of the words you can form by combining the letters A to Z, English is English words are a subset of those combinations. So dog, cat, corpulent, those are all combinations of those letters that form words that are English. Terzelfurky is a combination of letters from the English alphabet, but isn't actually part of the English language. It's not an English word. So language is a subset of all possible words over a given alphabet. That's what we're seeing here. So a regular language is defined as a language that can be recognized by a finite state machine. And so here we're going to have to go one step deeper and talk about, okay, what is a finite state machine? A finite state machine is it's a mathematical model of computation. It's sort of a theoretical model of understanding computation. And it's an abstract machine that can be in exactly one of a finite number of states at any given time. This I just copied and pasted from Wikipedia, but it's a fairly good formal definition of a finite state machine. But probably doesn't mean too much to you the first time you see it. I'm sure it didn't to me. So let's look at an example. A finite state machine is sort of a conceptual machine that you can express using circles and lines, basically. So The idea is that it's this thing that is at any one time is in a given state. And then from that state, when it receives input, it moves into another state based on what the input was. So say that we start in state 1, we receive input A, we'll move to state 2. If we receive input B, we'll move to state 3. If we ended up in state 2 and then got more input, if it's a C, that would take us to state 4. If it's input D, it would take us back to state 1. And so a finite state machine is just, it's this idea of a system that at any given time is in one state, which we usually represent as like a little circle, and then it receives input, which moves it into other states. And it turns out that you can model a lot of different types of computing tasks and scenarios this way with a finite state machine. And it has interesting theoretical properties, I'm sure, if you're a theoretician. So let's look at something more concrete. So a flashlight. If you think of a flashlight as a finite state machine, or the button in a flashlight as a finite state machine, we could represent it this way, right? The button has two states, or the flashlight has two states, right? Either on or off. In each of those states, there's sort of one type of input, right? Flashlights have like one input. You can press the button. That's the one thing you can do. So if you're in the on state, if your flashlight's in the on state and it receives the input of a power button press, then it moves to the off state. And in the off state, if it receives that same input, power button press, it's going to move back into the on state. So this is like a simple finite state machine representing that little system of a flashlight. It's got two different states, and it moves between those states based on different input. Does that make sense? Any questions about that before I move on? I can't even check the chat. Let me move over here and just pull that up just in case. I know some of y'all are shy. Okay, cool. So finite state machine, awesome. Let's look at one more example, and then we're going to tie it back to what we were talking about earlier. So television is a good example. So your TV has a volume system, right? And we could represent that by a slightly more complex finite state machine. So assume that your TV can be at volume 0 through 5. Super fancy TV, volume goes all the way up to 5. So say we start at volume 0, turn the TV on, the volume's all the way down, right? In that state, right, I can receive two different kinds of input. Either the volume plus up button is pressed, or the volume down, volume negative button is pressed. So if the negative button is pressed, I just end up back in the same state, right? I can't go below 0. So if you press the volume down when the volume's already at 0, you'll stay at 0. And if you press the volume up, you go to volume 1. If you press it up again, you'll be at volume 2. If you press it up again, you'll be at volume 3. And in each of these states, we see lines going back to previous states. So you press the volume down button, you're going to go back to a previous state. And once you get all the way up to 5, if you keep pressing the volume up, if 5 is the max volume on your TV, you'll just end up staying at volume 5. So it's a slightly more complex system than the flashlight, right? Because we have two different types of inputs. And we have some of these loops going on, which you'll see a lot in finite state machines, where in some states, receiving a certain type of input will just put you right back in that state. You'll just stay there on that type of input, which is another simple finite state machine. Slightly more complex. So let's go back to this definition. Why are we talking about finite state machines? Well, we're talking about finite state machines because I said that we had to talk about regular languages before we talked about regular expressions. So just trust me on that. So a regular expression, we said, is a language that can be recognized by a finite state machine. So now that we know what a finite state machine is, let's talk about what it means to be recognized by a finite state machine, right? That's just another way of saying that a regular language is a language for which we can build a finite state machine that can take a string that's in that language as input and will always end up in a valid state. So again, that's a little bit hand-wavy and abstract, but let's look at a concrete example. So let's think about a simple language, right? So if we wanted to find a language over the alphabet 0 through 9, right? So we're just looking at numbers, and let's say that the language we're looking at is names of spies who have a license to kill, right? So it is my understanding, and I'm not a huge James Bond nerd, but it's my understanding that the 00 part of 007 gives James Bond a license to kill. His spy designation is 007, and anybody who has a 00 at the beginning of their spy name has a license to kill, right? So if we just want to define as a regular language, names of spies who have a license to kill, it's going to be anybody who has a 00 at the beginning of their spy designation, right? So all of these 5 strings are different permutations of things in our alphabet, where our alphabet is 0 through 9, but only the white ones are valid in our language, right? Our language of spies that can kill you. 011 isn't. 1337 is not. So what would it mean to build a regular expression that can, to build a finite state machine that can recognize one of these, recognize whether any given arbitrary string of numbers is actually part of our language, is one of the spies who have a license to kill. So we might be able to write that finite state machine this way, right? We'd start in this circle over here on the far left, waiting for our first number, right? And if we get a 0, we move to the second state where we're still waiting for another 0. If we get a second 0, then we move into this final state where we just accept any numbers. As long as we get a 1 through 9, we're just going to come back into this state. So what would that look like for a given input, right? So say we're using 007 as the input to our finite state machine. We'd start in the blue state. We'd read the first 0, and that would move us into the second state. We'd read the second 0, and that would move us into the third state. And then we'd read the 7, and the 7 would put us back into that last state. And so because we read the whole input and we're in a valid state in our finite state machine, we say this finite state machine recognized that input. If we look at an input that's not in our language, right, and we try and run that through our finite state machine, again, we'll start at the left, we'll read in a 0, that'll move us to the second state. Then our input is 1, and there's no valid transitions between the state we're in and anything else on an input 1. So input 1 it's just not a valid input to receive in this state. There's no arrows coming out of this state for 1. And so our finite state machine will reject this input. It doesn't know what to do with it. It's not valid. So we have defined a finite state machine that recognizes this language of 00 agents. And so we can say that this language is a regular language, the language that is all of the 00 spy names. So that's how Kleene defined a regular language, right? As one that can be recognized by a finite state machine. And then Kleene came up with this notation so that you could express that type of finite state machine without having to draw a bunch of circles and lines. You could just express it textually. And that's what a regular expression is. A regular expression is a textual representation of a finite state machine that can recognize a regular language. So we can say a regular language is a language that can be recognized by a regular expression, which is equivalent to saying that it's a language that can be recognized by a finite state machine, because regular expressions are just basically another notation for that type of finite state machine. So that's a lot of theory. We're going to get into some more specifics now, but before I move on from the theory part, are there any questions about that? Comments, concerns? Checking the chat. It's about standardization. Michelle, so you had a question and then you said, oh, does that mean you don't have a question anymore? Or did you have a question about standardization? Going to take silence as a no. Okay. So So let's look at this regular expression here, right? So my assertion here is that this regular expression is equivalent to that finite state machine that we just looked at. It's expressing the same ideas. So let's break it up into pieces, right? So we have this regular expression. It's going to match these strings. It's going to recognize these strings here that are in white. That's the color, white. And then the ones in red, it doesn't match, right? Just like we saw with the finite state machine. So we'll start at the beginning. So in a regular expression, each of the characters is sort of, you can think of it as matching part of the input string, or kind of asserting something that's true about the input string. And some of the characters are taken literally, and some of them are kind of special characters that represent different aspects of the string that aren't like an actual character. So we're going to start with this caret sign, right? You've probably seen this before. So a caret in a regular expression matches the very start of a string. So it's not matching an actual character, it's just matching that concept of like wherever the string starts. So our regular expression starts out saying, okay, we're going to match at the very beginning of the string. We should see, two numbers, 0 and 0. And then any number between 0 and 9, some number of times, and then the end of the string. So the caret matches the beginning of the string, and we can see how the caret behaves by seeing what happens if we remove it. So if we remove that caret from the beginning of our regular expression, we'll see that now 1, 0, 0, 1 is matching, right? Because what's happening is the rest of our expression still matches 00 some number, right? But if we don't put that caret in there, it's just going to match it at the end of the string here, right? So adding the caret in forces that enforces that our regular expression has to match from the very beginning of the string. There can't be anything we don't expect at the beginning. Similarly, we have a $sign at the end of the string, at the end of our regular expression, saying that like the stuff our regular expression matches should go all the way to the end of the string. So there can't be anything funny at the end of the string we're not expecting. If we take that away, we'll see this 007X starts to match, right? Because we're matching 007, but then we're not specifying that like, and then the string should end right there after the 7. So this bracket part here, right? So the zeros should be obvious, right? Like the start of the string and then 2 zeros. So we're matching a string that starts with 2 zeros. And then we have these brackets and then 0 through 9, 0-9 in the middle of them. And what that is a character class. And a character class, where to match a literal 0, we just said 0. A character class is going to match any of a number of characters. And for numbers, there's this nice notation where we can say 0-9, put that in a character class bracket, and this will match any number between 0 and 9. So it's the same as doing this. It's the same as typing out a bunch of characters in the brackets. But when you're using numbers, you can add this little hyphen here so you don't have to type out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can see that we can add more than numbers in here. So if I add an X into this character class, suddenly X becomes a valid third or a valid character in this part of our string, right? And this 007X will start to match. So then the last piece of this regular expression is a plus sign. And a plus sign means that your expression can match one or more of the previous thing. So you put a plus after something to say that, yeah, I want to match one or more of that thing. So the thing that our plus sign comes directly after is this character class that we just talked about. So what our regular expression here is saying is that we're going to match strings that start with 2 zeros, followed by any number between 0 and 9, one or more times, followed by the end of the string. That's our $sign. So if we look at, the string 0, 0, for instance, that's not going to match because our character class has to match at least one character, one or more. So that's how this 0, 0, 1, 1 is matching, right? It's these 2 zeros match these 2 zeros, and then the 1, 1 are matched by this character class plus, right? because we're matching a 1, a number from 0 and 9 one or more times. In this case, we're matching 2 numbers that way. You can change the plus sign to a cleany star, which is just your little star or asterisk character. And the asterisk works in a very similar way to the plus, but instead of matching 1 or more items, it matches 0 or more of the previous thing. So in this case, we're saying, okay, we're going to match 0 or more of this character class, which is the numbers 0 through 9. So if we change the plus to a star, we see that when it's a plus, this double 0 doesn't match. We change it to a star, the double 0 starts to match, because it's now, our regular expression is saying it's now acceptable to have a 0, 0 followed by nothing, right? Followed by 0 other characters or 0 other numbers. So you'll use those a lot. The plus sign, the star, and these like character class brackets are some of the most common special characters you'll use in a regular expression. And the third one, we saw plus and asterisk. And the third one is a question mark, which matches 0 or 1 of the previous characters. So this is what we would do if we wanted to say that we're only going to match 3-digit spy names, right? So this would match 007, 000, but it would not match these longer ones like 0011, because this character class is now being modified by this question mark, which says it's okay if it's missing altogether, right? 00 is okay. It's okay if there's one of these things. 007 is okay, but it's not okay if there's more than that. We're expecting 0 or 1 of these numbers in this position, followed by the end of the string. Any questions about that? Chat. Okay, cool.
Trevor, I have a question.
Yeah, go for it.
What if the first 2 numbers are not matching? Is there some?
If the first 2 numbers in the input string don't match the regular expression?
Yeah.
Like these 2 zeros?
Yeah.
So in that case, the string, the whole string would not match the regular expression. So that's kind of this example down here, the 1001. It's red here because it doesn't match, and it doesn't match because it starts with a 1 and a 0.
Mm-hmm.
So you can think of, just like we had that finite state machine where you're taking like one item of input and then you're sort of trying to move to another state. You can think of the regular expression as that finite state machine, right? So you start in a state where you've read no input and you're looking for the beginning of a string, right? and you immediately find it, right? The beginning of the string is the first thing. And then you're going to get one character of input. In this case, it's going to be a 1, right? And you don't have anywhere to go. The only option you have right now is to read a 0, right? Because the regular expression has a literal 0 in there. So it's not going to match. The regular expression is just kind of bail at that point and say, okay, it doesn't match. But you can think of that like working through the string one character at a time is sort of how this regular expression is working. It's almost like you're writing a little program here, right? You're writing that little finite state machine just by writing out a bunch of characters. And you can think of the states as sort of being the space between these characters in your regular expression. So you read the beginning of the string, and then you're in this sort of intermediary state right here. And the 0 sort of represents like that arrow. That's that 0 moving you out of that state to another state. So you read in, the first character of 007, right? You read that first 0, and it moves you over here right before the next 0. And now the thing that's going to move you to another state, another valid state, is another 0. If you read one of those in, you move on, and now the thing that's going to move you into another state is actually anything between 0 and 9.
Okay. Well, I guess I have 2 follow-up questions then.
Yeah.
So it only moves from beginning to end. You're not allowed to like start at the end of a number, maybe? Like if you wanted the last 2 numbers to be 0 instead of the first 2 numbers?
Yeah, so you could do that. You could do that by, for instance, so we saw earlier, let me go back to this, the very beginning, right? If I take off this match start of string off the beginning, then my regular expression doesn't have to start at the beginning of the string. And so pretty much like anything is allowed at the beginning of the string until you get to 2 zeros.
Okay.
Right? So it's going to look for 2 zeros followed by 1 or more numbers at the end of a string. And so in that case, this one starts to match down here. This 1001 starts to match because we're matching this like 00 and one or more numbers at the end of a string.
Okay.
Make sense?
Okay. Yeah, that does. Thank you.
Cool. Okay, so any other questions? That was a really good question. Anything else needs clarification? All right, if you think of things, don't be afraid to interrupt. So now that we've seen a little bit about regular expressions, I'm gonna take a little side trail here and just talk about like how you would actually use regular expressions in JavaScript. Some of you may have seen this already, some of you haven't. I'm just gonna go over it to make sure we're on the same page. So this sort of idea of regular expressions is sort of a computer science theoretical idea that has been implemented in many programming languages. And JavaScript is no exception. JavaScript has a regular expression type built into the language to let you use regular expressions to match strings. So in JavaScript, the regular expression type, sort of like arrays and objects, has two ways that you can create it. You can use this new regular expression constructor and then just pass a string to create a regular expression object. Or you can use this notation just by using the, I always get the names confused, forward slashes as a delimiter, and putting the regular expression right in there. So it's kind of like how you can say like new array, right, to create an array, or you can just use the square brackets to like create a literal array. Same thing with regular expressions. So these two lines are equivalent, and they're creating a regexp, a regular expression object in JavaScript that represents this regular expression we've been talking about that matches 007. So once you have a regular expression object, you can do things with it, and there's lots of things you can do with it. The two that I'm going to talk about in this talk are both string methods. So it turns out that strings have methods that accept regular expressions and do things with them. So if I take the string 007, I could call the test method on it, pass it a regular expression object, and it will return true or false depending on whether that regular expression matches or recognizes that string. So I can do that to check and see that, okay, 007 is a valid name for a spy that has license to kill. 011 is not, that'll return false. So that's one way of using regular expressions to match or test against strings. Another way is the match method, which is another string method that allows you to match a regular expression. And it's going to return this sort of this match object, which I'm calling R here. I should probably call it M. I'm calling it R for response, but the response you're going to get back is a match object. And if the regular expression matches, then this object is going to resolve to true. And it is, this is wrong here. I don't know why I'm saying that. Sorry. Present. Ignore that slide. The R is not true, but it's going to return an object that looks a lot like an array that'll allow you to index into it. And if you look at the first index of this array-like thing that you get back, you'll see the part of the string that matched, right? In this case, the whole string matched, right? Our regular expression kind of specifies the beginning to the end of the string. So we'll see a 001 get back. So you can use the match that comes back in an if statement, because if the regular expression does not match, wow, I'm sorry. Let me just fix this right here because these slides are slightly wrong. So this is the, so in 007, in this case, the 0 is going to be 007, so you're going to get that back. In the case where it doesn't match, so this string does not match, in that case, this is going to be null. So if your regular expression does not match, you're just going to get null back from a match call. And if it does match, you're going to get an array-like object that has a lot of information inside it. And for right now, I'm going to point out that if you look at the first index of that array-like object, you'll get the part of the string that matched. And we're going to see a little bit later on how you can get other useful information about your match out of that object. So coming up soon. Okay, and then we're going to go back to see other aspects of regular expression. So any questions about the regular object?
Are they fairy dogs?
Sorry, did somebody ask a question? Nope, okay. Okay, so let's talk about other features of regular expressions. So grouping, let's talk about grouping. So imagine you wanted to match a string that was la, that's sort of any length, right? La, 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 la. You want to match anything that's just a repetition of LA, 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 right? So your first instinct might be something like this, right? LA with a plus sign to say I want LA one or more times. The problem with that is that in practice, it doesn't actually match any of those strings. What it matches is an L followed by an A one or more times, because the plus sign modifies the thing directly before it. And in this case, the thing directly before it is just the letter A. So we need some way to sort of group that LA together and say, no, apply this plus to like these two things together. We want to group them together. And we can use parentheses for that, just like you can in math, right? So if we put parentheses around the LA and then put a plus sign after it, now the plus sign refers to the thing right before it, which is this group of stuff inside parentheses. And this regular expression will match now LA repeated one or more times, and will no longer match the LAA. So that's super useful in regular expressions. Another useful thing that's related to grouping or related to the parentheses is capturing. So it turns out that when you use the parentheses, something cool happens called capturing. So in this case, I have a regular expression that's just I have, and then a character class here, 0 through 9 kids, right? So that's going to match a sentence like I have 2 kids. But what happens when we wrap the parentheses around that character class is that in the match object that we get back as our return from the match method call, if we look at index 1, right? So remember, index 0 is the part of the string that matched. And now index 1 is going to be the first capture, the first, it's going to be what matched inside the first set of parentheses in our regular expression. So in this case, we only have one set of parentheses, they're here. And R1 will hold whatever string matched that part of our regular expression, right? Because looking at the regular expression, we don't know. It could be 0 through 9. So just knowing that the string matched doesn't tell us how many kids the person has. But using that capture, we can capture that little piece of the regular expression and pull it out. So this would be really useful in like parsing input, right? If you know someone's going to enter a sentence like, I have some number of kids, you can use a regular expression to sort of parse out just the number, do something with it, right? So that is capturing. Any questions about capturing before we move on to not capturing?
Okay, so let's say you had 12 kids.
Mm-hmm.
Would we just change this number to like 0 through like 13, or how would that go?
So if you had 12 kids, let me pull that slide up. So if you had 12 kids, what you would do, if you wanted to match situations where people had more than 9 kids, right? Then you need to put a plus sign here, right? Just like before, so that you can have, because you want to think of this 0 through 9 as characters, right? So this will match the characters, any character that's either a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So if you want to match people who have like double-digit numbers of kids, then you could add the plus sign here to say, okay, I'll match any string where the number of kids is a 0 through 9 followed by another 0 through 9. Does that make
Awesome.
sense?
Yeah, perfect sense. Thanks.
Trevor?
Yeah.
So I was wondering, I noticed you said 0 is the match.
Mm-hmm.
How did you say, and then you said something about 1?
Yeah, so this match object here I get back that's stored in R is calling it an array-like object because it has a few different properties that arrays don't have. You can think of it as an array, and the first element of the array is going to be the portion of the string that matched. So in this case, it's going to be the whole thing. I have kids, and then the second item in the array at index 1 is going to be the part of the string that matched the first set for the first set of parentheses, right? And so maybe this is clear. If we add another set of parentheses, we could put parentheses around kids here. And that would give us a third element in our array that gets returned that would hold that kids string.
Oh, okay. Got you.
Yeah. And so you might have multiple things in your regular expression that are variable, right? So for instance, I might say, if someone's going to say they have 1 kid, they're probably going to say I have 1 kid, not I have 1 kids, right? So I might want to put a question mark after that S to say that the S can be there. There can be 0 or 1 S in this part of my regular expression, right? And in that case, if I ran this, I would have the whole match would be I have 1 kid, and the thing at position, the first capture would be the number 1, and the second capture would be the word kid. Does that make sense?
Yeah.
Cool.
Thank you.
Yeah. So, okay. So the next thing I'm going to talk about is I'm actually going to skip over here to reusing captures. So captures are useful because they allow us to parse out pieces of the regular expression after we've matched. But sometimes it's useful to be able to use the thing inside your capture later on inside your regular expression. So a good example is this situation here, right? Imagine we wanted to match a quoted word. And we don't care if you used single quotes or double quotes. We just care that you used the same quote at the beginning and the end, right? That's what defines a quoted string, is it has either double quotes at the beginning and the end or single quotes at the beginning and the end. So how would we match this? And it turns out, we can use a character class at the beginning, right? To match either a double quote or a single quote, followed by the string quoted, right? But then to match the closing quote, what we can do is we can use a \1, which references the first capture in the regular expression and says whatever was matched in the first capture of the regular expression, we also need to see here for this to match. So now that I say that out loud, I feel like that's a little confusing. So let me back up a little bit. So if we say we just did this the first way that you'd think of doing it, right, which is maybe put the same character class, the same character class at the beginning and the end. The problem with this method is that this character class matches a single or a double quote, and so does this one. So this regular expression will actually match this string with double quotes in both places. It'll match single quotes in both places. And it will also match a single quote at the beginning and a double quote at the end. Because these things aren't context sensitive, right? This character class just knows, hey, I can match a single or a double quote. So this last string here would actually match in this case. All these things would match. So what we want to do is we want to say, I want, whatever it is that matched here, whether it was a single or a double quote, has to show up at the end of my expression for this thing to match, for it really to be like a properly quoted string. And the way you can do that is wrap the character class or wrap anything in parentheses. And then just like we could say, you know, R sub 1 outside of our, you know, after our match, we'll get this object back that tells us like, oh, this was the thing that was in your first capture. You can actually reference the thing that was in your first capture inside your regular expression using backslash and a number. And that number just refers to which capture you're referring to. So \1 will match the first capture in your regular expression. And in this case, I just have one, right? And that will give us a match that matches the properly quoted strings that are balanced, but not this one that has like the wrong quote at the end. Does that make sense? Or should I try and explain that again?
Can you try to explain it again?
Yeah. Let's, you know what, let's do this. I feel like this is one where it's going to be helpful to have, it's going to be helpful to have a, no, not that. Let's do this. So let me get this a little bit bigger. Okay, so let's just open a node console. So let's say I have a string. String 1 is just going to be this string, right? So I'm using double quotes here so that these double quotes are actually part of my string, right? So if I console.log string 1, the quotes are actually printed out, right? They're part of the string. And then let's make a string 2 that uses single quotes. Oh no, I overwrote string 1 again. String 1 is that. String 2 is this one with single quotes. So if I console log string 2, right, I see it's got just the single quotes in it. And then let's do one last one that starts with double quotes and ends with a single quote and call that string 3. Okay, so I've got those examples here. And now let's make a regular expression and try and match them, right? So if I say string 1 that has the double quotes on it, right? And I can say match and give it a regular expression. Quoted. And then another character class at the end here. If I do that, I get this match object back, right? Which we saw is kind of like an array. And maybe for simplicity, I'll just use the test method here that will just give us true or false, right? Oh, sorry, I did that wrong. The test is actually a method on the regular expression. So you say regular expression dot test string 1. Right, so that gives us true for this first string. But if we try and test one of our other strings, and maybe I'll just write it in here. So if we try to test a string that has a single quote followed by a double quote, that's also going to match, right? Because this character class is happy to match a single quote or a double quote. And this character class at the end will also match a single quote or a double quote. So this regular expression I've written actually doesn't care if the quotes match. If I want to care that they match, then I have to wrap this thing in a capture. And let's just see what that would look like. Let's do this. I'm going to wrap that in a capture. I'll wrap both of these in a capture. And let's see what it looks like if we just look at that capture. So I have going to use string 1 and match against this regular expression where I have captures in both places now. And we'll see that in my capture, in my result here, as in index 1, I have the double quote that matched at the beginning of the string. And in index 2, I have the double quote that matched at the end of the string. Because string 1, just to remind everybody, has double quotes on either side, right? If I go back to this and I put in here a string that starts with a single quote and ends with a double quote, it's not going to match because I didn't add the D quoted, right? So in this case, right, it's showing me that, okay, your first quote was a single quote, your first capture was a single quote, your second capture was a double quote. So what I want to do is I want to write a regular expression that says, okay, the first thing can be either a double quote or a single quote. But if the first thing was a single quote, then I need to match a literal single quote back here. There's no choice. But if the first thing that matched was a double quote, then I want to put a double quote back here. So what I want to do is I want to put in my regular expression whatever it is that was captured in the first capture. And the way I can do that is just by saying \1, and that will put at that point in my regular expression whatever was matched by the first capture. So this thing, match \1. Is it different in JavaScript? Oh man, this should be working. Quoted. Oh, setback. Sorry, folks. I've got a syntax error in here and I can't see it. Let me Google real quick. Unfortunately, every language implements regular expressions slightly differently. And maybe it's just that the syntax is different. What is $1? Is this JavaScript? Shows to go, yeah. Content parentheses, listed groups. I feel like it should be the $, but that's not working either. So I don't know what's going on there. All right, I apologize. That's what I get from porting these slides from Ruby. So I actually don't know how you reuse a capture group in JavaScript. I'm going to have to spend some time and look that up because apparently it's not the same as in other languages. So let me look into that and get back to you. Quoted. I'll post something in Slack later today once I get that figured out. I apologize for that. That just feels very sloppy and unprofessional. I'm sorry. Chat. Okay, I'm going to move on for that right now so you don't have to watch me Google, but I'll follow up in Slack later today. And let's talk about alternation. So alternation is useful when you have two different things that could be valid at a certain point in your string, right? So let's imagine that we wanted to match all three of these strings down here. I have 2 kids, I have 3 kids, or I have no kids. So in that case, we want to match either, there are 2 things that are valid between have and kids. Either this character class, 0 through 9, right? Numbers 0 through 9 are valid, or just the word no is valid there too. So now people can say I have no kids instead of I have 0 kids. And to do that, we can use the parentheses again to create a group. And we can use this vertical bar which in this case represents semantically an or, right? Just like a double vertical bar in JavaScript will be an or in like a Boolean expression, like in an if statement. It has a similar role in JavaScript. If you put a single vertical bar, you're saying sort of this or that. So in this case, I'm saying, you know, the string should match I have space and then either this character class 0 through 9 or the literal word no. So you can use like parentheses in combination with this vertical bar to do alternation, to kind of have like different little sub-expressions in your regular expression that you can alternate, that either one can match and your string will match. Does that make sense? Would it be helpful to show more examples of that, or is that pretty clear?
That's pretty clear for me.
Okay, great. Okay, so let's talk about how regular expressions are greedy. Regular expressions are greedy. So imagine that we had this, this regular expression here, right? To something and beyond. And before we go any further, I have to introduce this dot character. So in a regular expression, a period doesn't match a literal period. A period is will match any character at all. So by saying here dot star, period star, it's a really common idiom in regular expressions to match 0 or more of anything. So it's kind of the most flexible match you can provide, right? So I'm just saying my regular expression starts with 2, followed by something, anything of any length, followed by the phrase space and beyond exclamation point. And you can see that I've got a question mark after this space and beyond group, saying that the and beyond is optional. So my intent here is to match any of these kind of things, right? Something that's to infinity and beyond, or just to the store, or to the store and beyond. Any of these should match, but what should not match is, let's just stay here, right? It has to be to somewhere. And I've got some captures in here, right? And you can imagine that I probably have this capture in here because I want to pull out of this phrase the place we're going to. So my intent is that on this first match, right, I should have infinity in my first capture group. And in the second one, I should have, in the second and the third one, I should have the store, right? So this capture group represents like the place that I'm going before I go beyond. So the problem here is not that the regular expression will match, but what shows up in each of these capture groups is a little unexpected. So what actually happens is that my first capture group matches infinity and beyond. And this second capture group, there's nothing. If I look at the third element in my match results array, r sub 2, it's just going to be undefined. And the reason for that is that regular expressions are greedy. So when I say dot star here, if you think of the little finite state machine that's sort of chunking through the input, it's like working through my string. It's going to start out and say, okay, I need a start of a string. Oh, great, I got one. Now I need a T. Great, I got one of those too. I need an O. I got an O. I need a 0. And then it's going to say, okay, now I need 0 or more of anything in the world. And so this dot star is just going to eat up all the characters left in the string because they all match, right? Infinity and beyond exclamation point is all a valid match for dot star because dot star matches 0 or more of anything. So it's going to eat up all of those characters, and then it's going to go, okay, what's the next thing I should expect in my string? And it's going to find this second group, and it's going to see that this group has a question mark after it. So it expects 0 or 1 of this phrase and beyond. And it's going to say, okay, great. I have 0 and beyonds here. I'm at the very end of the string. There's nothing left. And that's perfectly fine because this capture here, this group, is optional. So I'll just skip it. So it puts infinity and beyond in the first group, and then just skips the second one because it sees that it's optional. Then it finds the end of the string. So the regular expression matches, but the way that the captures happen is not really what we wanted, right? We wanted to get infinity in this so we knew where we were going. We wanted the and beyond to be optional, but sort of not part of our first group that we're capturing. Does that make sense?
So like you're saying, like the first set of parentheses captures everything because it has a star.
Right, it captures everything.
Okay.
And the term for that is that it's a greedy capture. It means that as the regular expression is sort of working its way through the string, each item, when there are these items that will match like 0 or more characters or 1 or more characters, they will match as many characters as they possibly can, while still making the regular expression match, right? So it's going to try and match the entire string, and then it's going to check and see, okay, I just ate up the whole string. Does the rest of the regular expression still match? And if it does, it'll just return and say, great, the thing matched, that's fine. I'll just put everything in this first one.
Okay.
Does that make sense?
Yeah, it does.
So, so to fix that, if we really do want to just match this infinity or the store portion, the way we would fix that is put a question mark after the star. And putting a question mark after a star or a plus sign makes that star or plus stop being greedy. So basically it's saying match 0 or more of anything, but match as few characters as you can while still making the whole regular expression match, instead of the default behavior, which is match as many things as you can while still making the regular expression match. So it makes the star not greedy, altruistic, if you will. So just by adding that question mark, the regular expression still matches just like it did at the beginning, but now our capture groups are the way we want them. The little regular expression engine started chugging through the input, and it got to this dot star, and it said, okay, I'm going to match as few characters as I can, as long as the regular expression match. So the first thing it's going to try and do is just match the I. Well, actually, the first thing it's going to try and do is match nothing, right? Because the star will match 0 or more characters. So your little finite state machine is going to say, okay, well, what if I just don't match anything here? I don't want to be greedy. I don't want to take more than my share. I'll just match nothing. Let's just move on to the next person in line, right? And so it'll move on to this next group, which starts with a space. And it'll see that, oh, the next character is not a space, it's an I. So the regular expression doesn't match. Let's back up and try and take a little bit more, right? So instead of taking nothing, we'll just take the letter I, right? I'll just take 1 character. Maybe that's enough to get the regular expression to match. And it'll then move on and find a space and say, well, the space doesn't match this N, which is the next character I'm looking at. So let's go back and I'll take a little bit more. And it'll take the I and the N. And it'll repeat this process, just eating 1 character at a time and then checking the rest of the expression until the whole expression matches, right? So it'll get all the way, it'll eat up a character at a time, infinity, and then it'll say, okay, I've eaten a whole word now. Let's see if the rest of the expression will match. And at that point, it'll see, okay, what I'm expecting next is optionally a space and then the words and beyond. And oh, golly gee, look at that, I have that. So we can move on. And so this first expression sort of very deferentially will like only take as much as it absolutely needs to allow the rest of the expression to match. Does that make sense?
It does. I was wondering, just out of curiosity, are regular expressions the same across all languages, or are they different? Since it's kind of separate.
They are almost the same across all languages. So it's a sort of a theoretical construct, right? That's been implemented in different languages, and it's usually implemented in a pretty standard way. There's a programming language called Perl, and Perl was one of the first languages to build in like really, really solid built-in regular expression support, just built into the language. Before then, it was the kind of thing that you might have to install a library, you'd have to write it on your own. But Perl had a regular expression engine built into the language, just like JavaScript does now. And it became sort of the standard implementation. And so you'll hear the expression PCRE, PCRE. which stands for Perl compatible regular expressions. And so a lot of language will sort of tout that they support Perl compatible regular expressions, PCRE. So that's kind of become a standard for regular expressions in languages. And so most languages, yeah, the regular expression support is very similar. Most of the stuff I'm talking about today, the caret, the dot star, this greedy behavior, the parentheses, the dollar sign, all of that is very standard vanilla regular expressions. As we saw earlier in my attempt to reference captures that were earlier in the string, it's a little bit more an advanced feature, and some languages support that and some don't. And it looks like JavaScript, if it supports it, doesn't support it the way that I expected it to. So it's a little bit of a mixed bag, but most things are going to be the same across languages. But you will find little edges where things are a little different.
Okay, that's good to know.
Yeah, it's a good question. Finally, let's talk about flags. So the other thing you can do with regular expressions is add flags kind of outside the expression. They're not part of the expression. Ooh, hang on. Let me go back. Before we talk about flags, I want to go back and talk about one other thing. So let's talk about not capturing before flags. So we've seen that the parentheses can be used to capture things. We've also seen that the parentheses can be used in alternation, right? With that, like, use the vertical bar to match this or that. So sometimes you get in a situation where you want to use parentheses in your regular expression, but you don't want it to actually be used as a capture. You don't want to capture that information. You're just using it for alternation. And what you can do is you can add a question mark and a colon right at the beginning of your group. And that will tell the regular expression, hey, I'm using this group, but I don't want you to capture it. Just ignore it. Don't put it in, R1, R2. Just skip over it when you're capturing. And so that would be useful in this other example that we saw where we talked about, where was it? When we talked about alternation, right? So in this example, we're using the regular expression here. We're using the parentheses to alternate, but we might not really care about capturing this this piece of information, right? And if we didn't care about capturing it, we could just add a question mark colon that would turn off that capturing behavior for this group, and this group wouldn't be captured. So the alternation would work exactly the same, but it's just not going to show up in our list of captures. And sometimes that's useful if if you're writing regular expression and you do want to capture something out of it, but you also want to use alternation in another place, and you don't want the introduction of alternation, the introduction of another group in your regular expression, to change all of the indices of all of your other captures, right? Since the captures are referenced just in order, sort of adding a group of parentheses is going to shift all of the parentheses that come after that in the order in your captures. So sometimes you'll want to be able to like have a group but not have it be a capture.
Okay.
So we talked about greedy, right, flags. Let's go back to flags. So flags. Flags come in handy in cases like this, where I want to match foobar, but I don't care about the case. Regular expressions in most language implementations will allow you to add flags, and often the notation is just like this. You just add a character after the closing / in your regular expression, and it just modifies the way the regular expression is applied. So in this case, the I flag makes the regular expression case insensitive. So just by adding that flag, we change from a regular expression that will only match foobar lowercase to one that will match it uppercase or mixed case or any combination of case. So it's another way to do a case insensitive match. There are, in JavaScript, there are 4 different flags. They tend to be pretty obscure. I is the most common one that you'll use. Another one you might use is the multi-line flag, and that's for cases like this. So going back to our double O regular expression from the beginning. So we have that regular expression, and we want to test for the presence of this this line of text, right? But we don't care if there are, and we need the, so here, sorry, let me back up and say that again. The string that we're matching is actually 3 lines of text, right? So it has this new line after each set of numbers, 007, 111, 123. So if we actually printed that out, it would look something like this, 007, 111, 123. If we printed that out and there were room, right? Our string kind of looks like this, right? It has these new lines in the middle. And sometimes you'll find that you want to match, we're looking for 007, but we don't care if there are other lines in our output. We're looking for a line that is 007 all by itself. And it turns out there's a flag called the M flag that will change our expression, our regular expression, to be a multi-line regular expression, or it'll turn on multi-line mode, however you want to specify that. And it will fix my slide. It'll change the way the regular expression is applied so that the $, instead of representing the end of the string, will just match the end of a line in the string. So as without the M, this is a false, this test is false, right? Because the $ matches the very end of the string. And this string is not 00 with some number followed by the end of a string. There's like new lines in here, those don't match, there's all kinds of crazy stuff going on. But if you add the M, this regular expression will start to match because the $ is now matching this new line, not the end of the string. So again, the M is something you're probably not going to run into that often. There are very few cases where I've needed to use this, and when I have, you're getting like really deep into regular expressions, but it's good to know about. You may see it come up. And with that, we are 10 minutes over, so I'm going to speed up. A note about character classes. We saw how to build a character class with the square brackets, where we did like square brackets 0-9 to get all numbers. Turns out there's some built-in character classes that you can use on their own. \s will match any white space character, so spaces, new lines, tabs. \d will match any number, so that's another way of saying bracket 0-9 bracket. \w will match any word character, so any number, letter, or underscore. So it's a good thing to match like variable names or that sort of thing. And then \b matches a word boundary, so that will match like a place in your string where it'll match like the end or the beginning of a word. If that makes sense. Just like $ matches the end of a string, \b will match the end of a word, or where the end of a word is defined by like there was a number in a letter, and then after that there was like a space or a punctuation or something. And then I just want to give a shout out here before we go to questions. There is a website called regexer.com, and there's a handful of these out on the internet. This one's fairly decent. That just gives you a way to like interactively play with a regular expression, and it will in real time. You can put some text at the bottom, a regular expression at the top, and it'll show you which parts of the string match your regular expression, which can be super helpful if you're trying to build a regular expression and you know the kinds of things you want it to match. You can put them all down here, right? So we can do 007, 008, but not 111, right? And then you can try and build a regular expression up here that will match those things, right? So it can be helpful if you're trying to like get a regular expression to work the way you want it to. Right. And with that, that is all my content. So anybody have questions, other stuff you want to talk about related to regular expressions?
I got a question.
Yeah. Mm-hmm.
So what would be a use case for a regular expression? Like, would you put them in a search function or something like that, or what are some use cases? I guess is what I'm asking.
Great question. You want practical examples? Picky. Yeah, that's a great question. Let's talk about that. So, regular expressions, probably the most common use, the first place you'll come across regular expressions is when you're doing input validation in a web app. Doing full stack JavaScript, the first place you'll meet regular expressions is probably in some sort of input validation. So imagine you have an email form on your site, right? You had a sign up form and people need to enter their email and their password, right? So someone's going to submit something in the form that's going to look like an email address, right? Trevor@me.com. It's not my email address. So you're going to get this variable email, right, in your route. And before you go and save it in the database, you want to do some validation to make sure someone didn't mistype their email address and leave out the @ sign, or they misunderstood and they just typed in their name in that field, right? So you need some way of saying, is this thing in email a valid email address? A regular expression is a really good way to do that, right? So you might do something like, all right, well, I know that an email address is, let's see, it's any letters, it's letters, numbers, and underscores, right? And we saw that \W is a character class that matched any of those things, right? So it's going to be some number of those, one or more of those things, followed by an @ sign, followed by some more zeros through, numbers, letters, and underscores. Let's see, followed by an actual period, and then followed by com or org or edu or co.uk. So something like that, right? So this is an email expression. This would be our email regex, right? So then we could test email addresses with this email regex by saying email regex.test. And if I test this valid email, it's true, right? But if somebody types in their name, we'll get false. If somebody just mistypes their email, Trevor@me, leaves off the .com, right? We'll get false. So regular expressions are really handy when you're trying to take some string input and do some validation on it to make sure that it looks the way you expect it to. Email regular expressions, by the way, are really, really hard to get right. Email, it's trickier than you think it is. So I encourage you, if you need to do email address validation, find a library that implements the regular expression. It's a page or two long, the actual a regular expression that will correctly validate valid email addresses. It's super complicated. A simpler example might have been a phone number regex, right? Where if you're having people enter their phone number, you might want a regular expression that matches let's see, we know that it's going to be the numbers 0 through 9, and there's going to be, let's see, -d is numbers, right? So it's going to be number, dash, number, dash, number, right? So that would be another good use case where you're trying to test telephone numbers that someone's entered to make sure it's a valid number. Something like this. So if somebody misses a number off of their telephone number, you'll know they're oh, that's wrong. That's not a valid number. So yeah, useful for that kind of thing. Useful for password checking, right? You might express your rules for valid passwords on your site with a regular expression. So if you say, I want passwords to be, can only contain the certain characters. So if you're passwords can't have spaces in them, you might have a regular expression that, here are all the valid characters I expect in a regular expression, right? A through Z, 0 through 9, and you can use exclamation points and underscores. And you have to have at least one character in your password, right? So this might be your password regex. So those are a couple of use cases. The other time you might use them is if you're parsing. So I had a job once where I worked at AT&T's Network Abuse Center. There's this email address, abuse@att.net. And most internet service providers have something like this, abuse at Comcast, abuse at, I don't know, whatever the other big internet service providers are. And it's an email address you can send an email to if you're getting spam from somebody with an AT&T IP address. So if you're getting spam from someone who is an AT&T customer, you can complain to AT&T and say, hey, one of your customers is using your internet connection to send spam. Please stop them. Or I'm getting hacked from some customer on your network. And it turns out that like routers and firewalls can be configured to automatically send emails to this email address, complaining about spam that they're seeing come in through the firewall or hacking attempts they're seeing come in through the firewall. So there's this little group of people in Raleigh, North Carolina that get hundreds of thousands of emails every year complaining about AT&T customers. And somewhere in that email address, there's going to be a time of day. And somewhere in that email address, there's going to be an IP address that sort of references like when the bad behavior happened and what IP address it was coming from. And so we had a bunch of software written in Perl that read through those emails and tried to find those IP addresses and those times of day to then go look up in our system who was using that IP address at that time of day so we could find the customer that needed to be, given a warning about please stop sending Viagra spam. And so we used a lot of regular expressions there for like parsing emails and trying to like, do some, it's almost like AI, right? You're trying to like read an email programmatically and pull out the relevant information. So that's another use case. Does that help? Kind of ground it?
Yeah, that was fantastic. Thank you.
Yeah, it was super helpful. The whole thing.
Yay. Well, glad to hear. Any other questions or stuff y'all want to talk about?
Yeah, can you not leave?
Unfortunately, that's not something I can accomplish. I'm going to miss you guys. I'm going to miss being here.
Yeah, we're all really sad.
Yeah, I'm sad too, to be honest. It was a tough decision. I wish that I could make it work, but unfortunately I can't. With my family right now, I can't move to Oakland and I can't shift my hours. It turns out that as much as I love being an SEP, it's really a job that I feel like I need to be in your time zone at least, if not in the room with you to do well. There's just so many hours of the day that I have to leave early, you guys are working and I'm already gone, or I'm working but nobody's around yet for me to help. And it's just a tough thing for me to do at this time in my life, long distance. So
yeah, but the times you're there are so helpful. Like, oh.
Well, it makes me happy and sad to hear that. But I'm going to try and I'm going to talk to Jeffrey. I'm pretty sure I can get them to let me keep my Slack access.
Mm-hmm.
And I know we've talked from time to time about like, I wonder if we get volunteers to come in and be like volunteer SCPs for, an hour here and there. And I might just make myself the pilot program for that.
That would be phenomenal.
Hang around as a volunteer because I don't know. I don't want to just not be involved at all. I love Learner's Guild and I love what's happening there. And I want to, I want to see you guys go on and succeed. And so.
Yeah, that would be so awesome if you could do that.
I will try not to drop off the radar altogether.
Yeah, please don't.
All right. Well, I'm going to call that a wrap for this lecture then. And I'll try and get the video of this up later today because I know some people couldn't make it since we were overlapping with a phase 3 lecture.
Awesome. Thank you.
Yeah.
Thanks, Trevor.
Talk
All
to you
right. Bye.
Bye.